Hi, this is Sudeep, and welcome to this session which explains the master slave concept in STAAD.Pro. While the term master slave reminds us of the most heinous episodes in the human history across the world where the fundamental rights were grossly violated, this is but a very important concept in the subject of computational modeling of structures and which defines a constraint relationship where one or multiple nodes in a structural model are tied to the deformation behavior of a particular node. But wait, before we go into further details, please hit the pause button for a moment and do me a favor by hitting the subscribe button if you are new, and do like this video irrespective of you being new or old to this channel. I'm sure you will find a lot of value. Okay, so let us see what this master-slave relationship is. Imagine a node M, which we call the master node. Now, this master node has displacements and rotations like any other normal node would, which would be dependent on the external constraints. Now, imagine this node S, which we call the slave node, and which is constrained to the master node M by a rigid link R. S does not have the freedom of movement like the master node, and all of its movements are dependent upon the movement of the master node because of this rigid constraint. So, if M moves towards the left, it would pull S along with it because of this rigid link attached. Again, if it moves towards the right, it would push S along with it. Similarly, if it moves up or if it moves down, it would pull the slave node S along with it. And if M rotates by an angle theta, the slave would traverse a circumferential distance of R multiplied by theta, where the R is the distance between the master and the slave node, and would also rotate by theta with respect to the global axis system. Now, the question is, how can we apply this understanding of master-slave constraint relationship in the actual modeling of the structure? Well, I'll show you one example today where this concept can be applied. Many a times, using this feature would need a subtle understanding of the structural behavior to correctly model a master-slave relationship. A mistake in the definition of the master nodes or the slave nodes in some cases can cause a gross deviation from the actual behavior of the structure in the field conditions. Okay, so let us have an understanding of our problem statement today in details to understand what exactly are we trying to simulate. So what you see on the screen are the directions of the global X and Y axis. So we have two white flanged W44 by 335 American sections as columns of a goalpost frame. A beam made up of American white flanged W40 by 149 section connects the columns face to face. The center to center distance between the columns is 5 meters, and the face to face distance between the column is 3.9 meters. The height of the frame is 3 meters. The column on the left is fixed at the base, and the column on the right is rotationally fixed at the base but is free to slide along the global X direction. And finally, the beam is connected to the flanges of columns using shear connections. That is, the connection would only be able to transmit shear and not the moments. And this is the top view of the structural system, where you can distinctly view the flanges and the web of the white flange section forming the columns, while only the flange of the beam is visible. Again, you can see that the face-to-face distance between the flanges of the column between which the beam spans is 3.9 meters, while the center-to-center distance is 5 meters. And now to the final aspect of the problem statement. The beam carries a load of 200 kilonewton per meter on it. So how do we expect this frame to behave with our knowledge on structural analysis in field conditions? Let us see. So what we see on the screen are the three elements of the goalpost frame standing in parts, and we intend to see the behavior of each element by drawing the free body diagrams of each of them. The total load on the beam will be given by the product of the uniformly distributed load of 200 kilonewton per meters and its span of 3.9 meters. Thus, the total load will come out to be 780 kilonewtons. Thus, the beam end shears will be calculated as 390 kilonewtons, and which would be transferred to the column flanges through the shear connection. Now that we have established the free body diagram of the beam, we are in a position to calculate its bending moment, which is calculated using the WL square by 8 formula for uniformly distributed load, and which comes out to be 380.225 kilonewton meters. And now we can see that the beam shear transferred to the column is acting at a distance of 0.55 meters from the center of the column, and thus this force will be converted to an axial load of 390 kilonewtons and a moment of 214.5 kilonewton meter on the columns. Establishing the free body diagram of the column section, we would get the uniform bending moment of 214.5 kilonewton meter throughout the section of column elements. So now we have established the behavior of the frame in the field conditions as per our understanding of structural analysis. All right, so most of us would have modeled the frame that we have in the real field condition in STAAD.Pro, like what we see on the screen, as center to center modeling. So the beam that we have modeled here spans from the center to center of column. So if we activate the dimensioning tools, we'll see that the beam span is 5 meters against the realistic 3.9 meters in the real field condition. For the specification, of course, we need to model the shear connections using the MZ releases at both the ends of the beam. We used fixed support specifications in STAAD.Pro to model the fixed support on the left, and to model the roller support on the right, we would use a fixed butt FX specification. Now, I have a detailed video on the support specifications where I have discussed both the fixed and fixed butt specifications. So I would suggest you to check that content out by clicking on the link above if you are not sure what the fixed and fixed butt support specifications are supposed to do. Finally, for the loading, we have modeled the uniformly distributed loads in STAAD.Pro using the member loads. Now that we have discussed all the various aspects of modeling, let us quickly run the analysis and let us go into the post-processing mode like this. Look at the beam bending moments. Let us annotate the beam bending moment results. Let us say maximum. And we see that the maximum beam bending moment comes out to be 625 kilonewton meters. Now, if you think about what we had achieved from the structural analysis from the real field condition, was that the beam moment should have come out to be 380 kilonewton meters. Now, this is a 64% increase in the beam bending moment, which would lead to an overestimation of the beam material if we are to use this particular simulation. Moreover, if you look at the column moments where we expected a moment of 214.5 kilonewton meters to be transferred, here we see that there is no bending moment in the columns at all. Now, this would actually lead to an underestimate of the column material. So, and one more thing, if we go into the reactions tab and if we look into the overall Fy moment here, we see that the total load is 1000 kilonewtons instead of 780 kilonewtons, which we had estimate from the realistic field conditions. Obviously, our modeling would need modification to achieve a more realistic simulation of the actual problem. But what is actually happening with this particular simulation that makes the results deviate so much from the realistic results? Let us find out. So what you see on the screen is the center-to-center modeling of the frame, where I have displayed the sections outline. Some of you might think that it is not right to have the top flange of the beam go beyond the top of the column. But if you think closely from the perspective of mathematical modeling, this does not distort the actual results. As a basic assumption of structural analysis, the load is always thought to be acting at the center of the beam. So as long as the beam center line is flushed with the top of the column, this creates no problem whatsoever. However, the distortion of the results that we are facing is due to the fact that the end of the beam is assumed to be connected to the center of the column, and thus we would need to take care of this distortion. We will see in a moment how the master-slave concept can help us solve this problem. But before that, we need to understand why are we getting the distorted results. So what we can see by our simulation is that the beam is spanning 5 meters center to center between the columns, and thus the UDL, instead of being distributed over a length of 3.9 meters, spans over a length of 5 meters, and thus we get the total vertical loads as 1000 kilonewtons instead of 780 kilonewtons. For the same reason, the maximum bending moment of the beam will come out to be 625 kilonewton meters, as it is being calculated for a total load of 1000 kilonewtons distributed over a span of 5 meters. And finally, since the end of the beam rests on the center of the columns, a shear of 500 kilonewtons will be directly transferred to the center of the column, and thus there will be no moments transferred to the column. So we now understand why we are getting the distorted results with this particular simulation. Now let us see how we can model the same structure using master-slave to get the expected results. So the same frame that we had modeled before has now been modeled like what you see on the screen in STAAD.Pro. Let us have a better look of this model from the front. Now, let us activate the dimensioning tool to see the distances that has been specified here. So the center to center distance between the two columns has been specified to be 5 meters as before. However, in this case, the beam has not been defined from the center to center of column. Instead, it appears that the beam is dangling in the middle, and if we actually see the distance from the start of the beam to the end of the beam, it is 3.9 meters. So at least for the start, we can say that the dimensioning here represents what exactly is in the real field condition. Now, let us deactivate the dimensioning view and the support view from the so that we can have a clearer view of the models that has been defined. Let me switch on the node numbers so that we can clearly understand what nodes are we speaking about. Now, from the first look, the model would appear to be completely disjointed, right? The beam would appear to be dangling in space without any support, and the two columns are, standing isolated from each other. Well, that would have been the case if we had not defined a master-slave relationship. So how did we define the master-slave relationship? Well, to find that out, you need to go to the specification option, and you can see that there are two master-slave commands in the specification whole structure box. So in order to view, highlight the master-slave in the model, you have to click on highlight the assign geometry, and we select on the first master slave option. Now we will see that two nodes has been highlighted here. Now let us activate the magnifying glass to have a closer look at those nodes. So we can see that node number 2 has been highlighted in a peculiar way, where it has been encircled with two concentric circles. This is an indication that in the master-slave relationship, node number 2 is the master node. And we can see that node number 5 has only been plainly highlighted, which means that it's a slave in the master-slave relationship. Now, if we select the other master-slave command from the specification whole structure box, we would see that another set of nodes has been highlighted. And if we again zoom in to those particular nodes using the magnifying glass, we'd see that node 3 is the master node and node 6 is the slave node. So then what is it that we achieve by defining this master-slave relationship? Well, let us see. So as we said before, though the structure appears to be disjointed, internally STAAD connects 2 and 5 and 3 and 6 using rigid members, and thus the structure will be treated like this. So you can see that in the internal consideration for STAAD, the structure is perfectly jointed. The load is considered on this beam spanning 3.9 meters only, and thus we are not overestimating the loads. Thus, considering the rigid links, the free body diagram of the whole frame will look like this with all elements separated. The beam would span 3.9 meters, and thus the total load on the beam would be 780 kilonewtons. Thus, the beam end shears will be calculated as 390 kilonewtons, half of the total load. The rigid link representing the stiffness between the center of the column to the face of the column and its span would represent a distance of 5.55 meters, which is the distance between the center and the face of the column. The beam end shear will be transferred as a load on the rigid link, which would lead to the development of a resisting force and a moment. The moment would be calculated as 214.5 kilonewton meters, which is equal to the couple developed by the two equal and opposite forces. Now, the force would be transferred to the columns as axial loads and moments on the column, and the free body diagram would be complete with the support developing the necessary resisting forces. So we can see that by invoking the master-slave feature in our model would simulate the behavior that we would expect in the field conditions. In this case, however, we understand that since it is only about the rigid link between the two nodes that would solve the problem, it does not matter much as to which should be the master and which would be the node in this relationship. In the forthcoming episode on advanced topics next month, where we will discuss about rigid diagrams, we will show the importance of the precision of the definition of the master node and the slave node. Anyways, let us get back to our STAAD model. So now that we have defined the master-slave relationship, let us run the analysis of this particular model. And once the analysis is complete, let us go to the post-processing mode. And if we go to the reactions tab, we would see that the total vertical load is now 780 kilonewtons as expected. And if we go to the beam results, we can see that the bending moment appears to be consistent with what we had expected from the real field conditions. So let us annotate the results. Let us annotate the bending results, the maximum bending results. Click on annotate, and we see that for the center of at the center of the beam, we get the maximum beam bending moments as 380.25 as expected, and we get a uniform moment distribution along the column cross sections, and the value is 214.5 kilonewton meters as we had expected in the field conditions. Finally, I'd like to quickly show you how to define master-slave. Now that we have understood the implications of using master-slave, just a quick demonstration on how you could define a master-slave in this particular model. So you need to go to the specification option and click on the node, and you can, the first option is master-slave. So you have to select the master node. In our case, let us select the master node as this one, node number 2. So we'll say node number 2 and click on add, and then we need to assign this to the slave of that master node 2. So let us use the cursor to assign option, and select on node number 5, this would mean that node 5 is now constrained to node number 2, which is the master in a master-slave relationship. Similarly, for for the other end of the beam and the column, we again define a master-slave relationship. In this case, the master node is 3. So we click on add, and once that is done, using the assign to cursor option, we can select node number 6, and thus the master-slave relationship is defined. Now, if we highlight the assign geometry, click on the first option, we can see that node 2 and 5 has been defined to be in a master-slave relationship, where 2 is the master node and 5 is the slave node. Similarly, for node 3 and 6. If you go into the text commands of the file, the master-slave is defined using these values, these commands, where you say that slave and the master slave constraint is rigid, master node is 2, joint number 5. Similarly, the second command indicates that master is 3 and joint number is, or the slave joint is 6. Joint 5 and joint 6 means the slave node specifications. So you can see how the master slave can be intelligently used to solve field condition. I could show you only one case today. In the next episode, I intend to show you how the master slave feature can be employed efficiently to model structures for seismic analysis. Please do me a favor by hitting the like button and comment below on anything you have a confusion with, or if you want me to make a video on. So thank you for listening today, and see you in the next one.